This one. Okay, good morning. That's great. Thank you. It's great. We have professionals in the audience today, I can tell. It's really great to see all of you here today. I am Nadia Mason, director of the Beckman Institute, and it's a really great pleasure to welcome you and to the Smith Group lecture. This is our first in-person Smith Group lectures since the COVID-19 pandemic. And it's just really great to see everyone here today, especially since we have an even more than usual special treat in our speaker, and I think you'll really enjoy the talk. So this lecture is made possible by the architectural firm Smith Group. The firm is the one that designed the Beckman Institute, and the firm is rightfully proud of the project. Even 30 years later, this building is still beautiful and functional for those of us who live here. And I have to say that every visitor that I bring into the building walks in, the first thing they say is, wow, such a nice building. And I think it's really impressive that even after 30, 35 years, we still elicit that response, the architecture, the beauty, the form, and the function all combined in the Beckman Institute. So Smith Group endowed this lecture in honor of the Institute's founding director, Ted Brown. And I want to recognize the Smith Group representatives here today, Rana Lee and Hans Thummel. They've joined us for the lecture, and we really appreciate your generosity, the fact that you're here, that you've been here consistently supporting the Beckman Institute and supporting especially this lecture series. So now I'm pleased to introduce the former Beckman director, Jeff Moore, who is going to introduce today's speaker. Jeff.
Thanks so much, everyone, for coming out. I'm Jeff Moore, as Nadia mentioned. I had the true privilege of serving as the director of the Beckman Institute from 2016 to 22. And one of the last things I had to do was to line up the speakers for the successive year, and I was really fortunate that I was able to convince Joe, and even though the travel schedule was quite amazingly complex, with Stacy Olson's help, we were able to make it possible for Joe to come and give this Smith Group lecture. I need to set the context here, and so just if you would bear with me for 3 to 5 minutes, because I think the context is super important from the standpoint of why Joe was the right person to come and give this lecture. His biography, as you'll hear, is truly amazing, but I've had the pleasure of knowing Joe since really his first days at the University of North Carolina, Chapel Hill, because we began our independent careers together. And at that time I was at the University of Michigan, and I think I invited him to the University of Michigan to give one of his first outside lectures. And we've traveled a lot together, and when you travel together, you know, you ride in boats or trains or airplanes or cars, and you get a chance to have those long conversations with people, and you really do get to know them. And so I think it's important that you know that as I'm delivering this, it really comes from a true knowledge of the person who you're going to hear speak. It's really fun to look back at how in the past 30-some years those early conversations have played out. And Joe has really impacted the world by, I would say, putting science into action. Early on, he understood, and this is what makes him so perfect for giving the Beckman Institute talk. Early on, he understood the value of interdisciplinary collaboration, and even more importantly, and for all young people in the audience, this is critical, being able to pick the right problem at just the right time. And Joe has nailed the timing over and over again. As I think you'll hear, Joe is really forward-looking. He will, better than anyone, I think, create form and function using a beautiful combination of materials, of chemistry, of engineering, and simulation. And he brings that into customized manufacturing needs. So a little bit about his academic background. Joe is the Sanjeev Sam Gambar Professor of Translational Medicine and Chemical Engineering at Stanford University, and he holds appointments also in radiology and chemical engineering. As I mentioned, he was previously a professor at UNC Chapel Hill and NC State, where he was a chemical engineering professor at the time, since UNC didn't have an engineering program, and that was something that he recognized as vitally important. He reached across the triangle and found a partnership with NC State. Joe's responsible for numerous breakthroughs in the areas of green chemistry, medical devices, nanomedicine, 3D printing. He's published more than 350 scientific articles, and he's been named inventor on over 200 issued patents. Additionally, he has mentored more than 80 students, and I would have to say, if you ask Joe, one of the things he's probably most proud of is the fact that over half of those are women and underrepresented groups in STEM. Joe's research, and really this idea of delivering science into action, has put him at the highest pinnacle of entrepreneurial success. And I need to pause right here and say that in 1990, when Joe began, the idea of a professor being an entrepreneur and pursuing really startup companies was a pretty foreign idea at the time. I won't say that it hadn't been done, it certainly had, but it wasn't anything that was kind of almost, has become maybe an expected mark of success today. And so there's this always push to think about how can I translate my science today into research. But in 1990, this was pretty much unheard of, and certainly there was no playbook. And many people have tried to play out that journey and failed. And Joe, as you will hear, not only figured out how to navigate that, but he did that successfully time and time again. His work, as you'll hear today, led him to really start up the company Carbon, and it's based on the technology that is really going to be the emphasis, I think, of most of what he'll speak to us today about. But before Carbon, he was a seasoned entrepreneur. In the 1990s, he developed an environmentally friendly manufacturing process that relies on supercritical carbon dioxide instead of water, and the biopersistent surfactants for the creation of fluorinated plastics. And Joe's lesson learned, which we learned about last night, was really to take ownership of your technology and bring it into practice yourself. Don't rely on big industry to try to carry that out, because they may have alternative motives. He is the co-founder of biosorbable vascular solutions to commercialize stents. With his students, he's developed nanoparticle fabrication technology, which when he first described it to me, I know I didn't ever get a sense of the level of enthusiasm until I met Joe in his office, and he talked about the print technology, particle replication, and non-wetting templates. And that led to the co-founding of Liquidia Technologies. Joe has an amazing talent for changing his focus, and I think that's a key aspect of success, because it's that changing focus that gives you constant learning over time. And Joe has never stopped learning. And throughout his career, I've watched and admired by that ever-progressing evolution of his career. He's also an incredible leader, and I saw this more than ever from a distance when he was leading Carbon, both in the early days and through the pandemic. And it was 6 years of his life that he devoted to really all those lessons learned both in the lab and as an entrepreneur that he put into practice as a leader, and an incredible one at that, where he valued people above anything else. And when you value people, I think you'll get the most success out of your technology. And I thought that's what I saw in Joe's experience at Carbon. The other thing I learned from Joe, and I especially became aware of this during the time that I was director, was the importance that he put in his leadership role in diversifying STEM. And he taught me a lot of lessons as I monitored him from afar. And what an important challenge that we have before us to put our country in a solid position by making sure that we have a diverse audience, a diverse collection of science and people at the lab bench and in technology. Joe's one of 25 people who hold membership in all three of the national academies, the National Academy of Medicine, the National Academy of Science, and the National Academy of Engineering. And in 2016, he won the National Medal of Technology and Innovation. So Joe's interest in interdisciplinary collaboration and his nimble approach to both science and technology, which of course is the name of the Beckman Institute, Beckman Institute for Advanced Science and Technology, fit perfectly within the mission and the core values of the Beckman Institute. And Joe, I am so pleased that you could join us today for the Smith Group Lecture.
Wow. Maybe I shouldn't give a talk and we just go to questions. That was an amazing introduction, Jeff. And when you have your friends invite you back, we've been at it for a long time. And it's really great to see you thrive here and help elevate what was here. And now that we see the future, a legacy is not worthwhile unless there's a great future to drive it. And it's great to see the handshake and the handoff here. So thank you for the invitation. And I'm glad it worked. And we're almost there. Great. Thank you. Appreciate that. So as Jeff sort of walked through some things, 30 years at UNC Chapel Hill and 25 of that with NC State. We think a lot about entrepreneurial things, and most of these activities have been driven by former students and coworkers, and from green chemistry work to nanomedicine and biodegradable stents and a battery company in the East Bay called Blue Current. Local drug delivery using iontophoresis for driving drugs into poorly vascularized tumors for pancreatic cancer, and at-home tests in the privacy of your home for women for cervical cancer, and microneedle company for taking continuous glucose monitoring to the next level with lots of molecules. All these activities were led by other people. I had hired a CEO to launch Carbon, and the investors asked me to lead it after a little while, and I told them all the reasons why it's terrible to have faculty lead companies, and they still want me to do it, and I agreed to do it for a year, and so they can get rid of me gracefully. Ended up doing it for 6 years, and ended up having to shut down my academic program, but I got my life back, as I tell people, and stayed on the West Coast this time, and friends at Stanford called, and during this time also joined the board of the National Geographic Society, which is fun. It was my internet growing up. And I chair the board of my alma mater, Ursinus College outside Philly. At the end of the day, this is all about student achievement for the most part. And at Chapel Hill, my group was 90% chemists, 10% engineers. At Stanford, it's just the opposite. And Nancy's happy about that. And I got a double E, ME, Bio-E, Mat-Sci, Chem-E, and a few chemists. Great group of undergrads, a few postdocs, and highlight one of your own, Kai Nguyen, and she got her PhD with Charles, and postdoc with me, and now I think it's official. Yep. She's joining the faculty at Texas A&M University, which we're really excited about. A great group of staff and team, and Eileen helps with the coordination. And the lab is funded by the Bill and Melinda Gates Foundation, heavily Wellcome Leap, NIH, and some internal support. A lot of great collaborators at Stanford, and you meet new friends and build relationships. And I'll heavily talk about some stuff Eric and I are doing. Kurt's a big part of our group now, and a lot of work with Jonathan Smith, who's at VLP Therapeutics, and Heinrich Jaeger, University of Chicago. I'll show some of his work. To start off with, you'll find this on our website. These are the values that our group has focused on and want the world to know about. And we say this to be clear that we want our lab to be a destination for excellence wherever it can come from. And so for people to feel included, and I think it's increasingly important to be clear about that as you set up your labs or your organizations or whatever you're associated with. So feel free to read more about this on our website. Making things. A lot of us are familiar with manufacturing and making things. Manufacturing is a $12 trillion marketplace. Polymeric products is $1.1 trillion of that. 30% of that's injection molded, about $300 billion. And those molding techniques are the way most people make things. Heat up a polymeric material into a liquid state, drive it into a cavity, let it cool down, either vitrify or crystallize, and you get the part out if it has the right symmetry. But very limited opportunity for design. Subtractive techniques, think about milling, CNC machines, start with a block and eliminate materials. And what we're talking about today, and everyone's familiar with 3D printing, is an additive technique. I think, when I think about additive, the things I think mostly about, what you can make that you can't make by the other techniques. At the end of the day, that's what drives value. And lattices are a great example. This is a beautiful building. The architects are here. They've got a lot of struts in this building. And Eiffel Tower, bridges, struts are a great opportunity, but they're assembled. Imagine being able to make something that's got 14,000 struts in one piece. This is the world of additive manufacturing. And it opens up new products. And to say something very simple, but I think it's really profound, you don't buy stuff unless people can make it. It sounds a little silly, but if you can't make it, you don't buy it. Which says, there's huge limits on design because of our methods of making. And I don't want to confuse that between a prototype and a product. We in science and research do a lot of things to make amazing things, to either prove a point, understand something, opens up new insights. It plays a really important role. But let's not confuse manufacturing science with one-offs. They're different disciplines in many ways. And I want to focus on the manufacturing science and what that can open up new opportunities. I borrowed this slide from Matt Becker at Duke. I don't want to talk about Duke very much, but Matt's a good guy. And the Tar Heel runs strong in me. The polymer additive manufacturing perspective from Matt's eye, materials extrusion techniques or direct write techniques. And then you see variants of that here in new approaches with frontal polymerizations and other things for making things directly. There are powder sintering technologies out there. A lot of this emerged from the metal-based world and moved into polymers. Opens up, some great examples and probably, some of the highest volume products or things that people think about. People have been trying to get materials made this way. And then the light-based vat polymerization, where the light was used in a direct write approach in the beginning, referred to as a SLA process, stereolithography. And then light in 2 dimensions instead of direct write from a DLP projection system allowed the process to go faster and an approach doing that. These processes were invented in the 1980s in Japan and then commercialized by 3D Systems and others. And then what I'm going to talk a lot about, and again, this is Matt's slide. It was nice to see him organize things this way. But our continuous liquid interface production process, which is a variant on SLA that I'll walk you through. And then I'm going to use CLIP as a look back to what we did at Carbon, and now I'll look forward to what we're doing at Stanford and trying to commercialize is new approaches for CLIP. And I'll walk you through that as we go on. So our approach for thinking about this was a variant of a DLP process where we're using light in 2 dimensions from a DLP projection system at 385 nanometers. We're projecting light through a window that's at the bottom of a reservoir for at least a partially UV curable resin. And it will lower a platform into this resin. It'll get very close to this window, and then we'll start to irradiate 2-dimensional patterns. And the part will adhesively bond to this platform, but not to the window, because the window is not only optically transparent, but it's permeable to oxygen. Oxygen inhibits the photochemistry that the light is triggering, and it never bonds to the window. There's always a liquid layer. And so that asymmetry in creation in the z-axis allows us to start pulling the part out from the reservoir, as illustrated in this video. It's an accelerated video. But we're going to make a complicated part that actually its form factor is not easily moldable. Platform lowers, you'll see light in 2 dimensions, which is an XY cross-section of this part. And we're beginning to bond this part to the platform and then pull it out. And there's a gap between the part and the window that as the part gets pulled up, it's creating a negative pressure and drawing liquid in underneath it. And this resin renewal is a mass transport advantage over the part being glued to the window, and you have to fracture it off the window, pick it up, and introduce new resin. So it's a mass transport facilitator of this process. And it allows us to use light, and it allows this process to go 100 to 1,000 times faster than a traditional SLA approach. And the keys to this, I'll walk through some elements of this. First, the window. The window is, in a first variation of this, an amorphous fluoropolymer, a copolymer of tetrafluoroethylene, and it's fluorinated dioxyl monomer that breaks up the crystallinity of polytetrafluoroethylene. And so it's an amorphous glass. And this material is the most oxygen permeable material known. And a lot of people are looking at it for all sorts of separation examples. But it's also not soluble in organics. It's photochemically very stable. It's an amazing material, and it's perfect for this process. And that allows oxygen to come through, and the organic doesn't dissolve into the window, right, as it would for silicones and other materials. And this allows this process to run. So I'm going to show you something. This is an optical coherence tomography image of a part growing. So it's kind of like ultrasound imaging, but it uses light rather than sound waves. And we put some particles in there so you can see it as a contrast agent. And you can see this part growing, color-coded to guide your eye. And you see the resin being drawn into this gap as we elevate the part. And it's just caused by the negative pressure pulling the resin in. And this allows resin to be renewed at the build surface. This gap is created, well, first of all, this mauve color, the polymer, is being created by light. The resin's got a photoinitiator in there that decomposes, creates radicals, but it doesn't polymerize in this zone because oxygen's replenishing. And so let me explain that in a little more detail. This is a generic concentration axis down here, and then this is the z direction from the window up into the resin, from the window up into the resin. And so, and we have a liquid resin that's got a polymerizable monomer and a photoinitiator. We have light coming through the window. Light is at its most intense in the resin as it exits the window, because that's the source of the light. And then the light intensity decreases with distance up into the liquid just due to the molar absorptivity of the resin. It's like shining a light into murky water, right? It's dissipating with distance. That light is decomposing a photoinitiator that's generating a radical pair. So the concentration of radicals basically tracks with the light intensity. And everybody that does free radical polymerizations knows that, like, the first thing you typically do if you're doing a free radical polymerization in a round bottom flask is you degas your monomer. What are you doing? You're removing the oxygen. Because if you generate a radical in the presence of oxygen, the rate constant for reaction with oxygen is far greater than initiating a polymerization. Right? That's why it's easy to ship monomers around. They don't, they're inhibited, but they're inhibited by oxygen and any added inhibitor. But you degas your monomer, you don't want to ship that around because that can prematurely polymerize. Well, here, that radical is consuming the oxygen. But we have an asymmetric way of replenishing the oxygen. So there's a chemical equilibrium that's trying to be reestablished, and we have a gas permeable membrane. Oxygen's coming back in the Z direction. But as the oxygen concentration decreases as a function of distance, we get below a certain threshold and a polymerization will take place. And if it's a cross-linking system, molecular weight will go to infinity. There's a polymerization gradient that's happening, but this is the dead zone that we study, okay, that distance. And we've mapped this out in great detail. And it took a lot of studies, and we're constantly adding to our understanding. But we have a liquid flow into this dead zone. You can have non-Newtonian and Newtonian fluids, depending on what kind of monomer systems you're using. We have a velocity flow field into that gap. We have complete, exquisite control on all the mechanical operations of the printer as a function of time, and the light and everything. And so this is an axis of time. This is stage position. We have the printer platform at a certain stage height. We move it at a certain rate with a certain jerk, at whatever way we want to control it. We can stop the stage. As liquid is being drawn in, we can wait till the liquid gets to the deepest pixel and reaches quiescence, and then we can photolyze, and then we can repeat the process. And as a cross-sectional area is changing dynamically, we've got this all controlled. I think of this as a software-controlled chemical reaction to grow parts, okay? And you can screw everything up, but we've figured it out. And we built a printer based on the subdiscipline of engineering called mechatronics, where every aspect of this printer has been software controlled, motorized, sensored up, oxygen control, everything. It was a hell of an investment of a piece of equipment so that we could do over-the-air software upgrades every 5 or 6 weeks. And the printers were getting better and better. And our customers saw real improvements in printing process or printing speed or the introduction of new resins, because every resin's different. Every resin's got a different viscosity, different dose to cure, different mechanical properties. There's a lot of forces on the part as we're trying to push the speed of the printer. You could start putting these printers together into mini factories. The platform now has a near-field communication tag on it, and it knows which printer it's in. And now we're starting to track things through the factory and build the software for tracking things. Every window is actually not identical. We build them within a nominal spec. Every window's got a near-field communication tag. We build the windows within a nominal spec, then we do a bunch of measurements, and you put that window into that printer, it pings the cloud and brings down specs just for that window, so that it prints perfectly. You can start envisioning bigger factories, and then you can start to build them with bigger printers. This is our factory in Shanghai. And then, when you print a part and it's got excess resin on it as it's printing, and I'll show you the chemistries here in a little bit, you want to get that excess resin off. You can't afford to wash things at this scale. So we developed basically a salad spinner. You'll see a platform, a robot will come in and grab it. You'll see a pair of shoes. It goes around in a centrifuge, and that excess resin is flung off, collected at the bottom, and goes back into the printer. So there's no waste, and there's no mixed waste generated with solvent. These parts all have a near field or a digital indicator on here, and every part is tracked in the factory. And in fact, we do stress strain curves on every part or any other kind of analytical. I think of every part as alive. Every part has a unique record in the cloud. We know its born on date, which printer, which resins, which operator, which location. We know its grades in school, right? We know its death certificate, and now companies are looking at recycle and all data tracked environmental stewardship in that opportunity. let's talk about the chemistry. So we have a printing process that's really fast, but most light-based photochemistry, polymer chemistry, leads to brittle plastics. It's hard to get a great material out of a light-based process. And so this is where we had to figure out how to do this well. And we basically broke it into two problems. And we developed what we refer to as dual cure resins. So we have a resin that is we keep it photochemically curable and shapeable. But a lot of the best polymers are made by reactive liquids. Think about epoxies and polyurethanes, polyureas, silicones, cyanate esters, you name it. Mixing liquids come together, highly reactive systems. No one in 3D printing went down that direction because the printers were too slow and the resins would prematurely polymerize. But because we're going 100 to 1,000 times faster, we knew we had a window of operability. And so what we did is we combined and did orthogonal chemistry. So just like Carolyn Pertozzi just got the Nobel Prize in orthogonal chemistry for doing chemistry in a cell without screwing up a cell, this is orthogonal chemistry in the printer. And so what happens is, and I'll give you through a couple examples. Let's talk about epoxy chemistry. Epoxies are diapoxides and diamines. And we added a free radically curable system and a photoinitiator. And we keep these two separate so we could ship them off because you don't want the amines and epoxies together. When you buy an epoxy glue, you go to a grocery store, it comes in 2 tubes. So even engineers can make polymers, right? Because they've got this, I'm kidding. It's a bad, this is a silent crowd. Where are the chemists? Chemists, give me, yeah, chemists. Why don't you guys laugh at that? Come on now, you see the ratio. I need help. The stoichiometry is balanced for them. And that's what we do. And then you mix these reagents, you put them in the printer, you set the shape of the part. There's a little bit green color here. This is the green state. Doesn't have great mechanical properties, but it's sitting here with this other chemistry. And then we heat it up and drive it to full cure. And you can keep control of the stoichiometry and the functionality. You can get linear materials, you get cross-link systems. This is a great way to get a part. Now, when you do the light-based process, you typically wash it here, get all the excess resin off before you kick off the second stage, or you spin it in an environmentally dry process. This led to the first 3D printed parts ever on a production vehicle out of Detroit. Despite 3D printing being around forever, we were the first to get parts on Ford Mustangs, F-150 trucks. And these are these epoxy systems that reduced lead time. They were lighter weight. They competed with glass-filled PBT and amazing parts in a lot of different vehicles. We love to travel to Italy. And we landed all the performance vehicle companies there. Lamborghini is an amazing company. Think about this big part right in the front. Imagine if you had to make an injection molding tool for that big air duct that's unique to that vehicle. They don't sell a lot of Lamborghinis, right? So let's assume they sold 3,000. It's probably less than that. But you'd have to cut an injection molding tool for that part. This is made with light, moldlessly, having the right properties. And it allows them to really innovate and design properly. But to hit the automotive standards, you really need to hit a lot of properties. And this took us 2 years to get this through Ford quality standards. And that's sort of like a badge of honor, and then you can move the chemistries into all sorts of other vehicles and suppliers. Every new resin opens up the TAM, the total accessible market. And so as you introduce flame retardant resins, it opens up new applications. And so we look for new resins that can open up new worlds of opportunity based on performance. Cyanate esters. So those are all epoxy systems, all those automotive parts. Cyanate esters are amazing materials, amazing chemistry. Mostly microelectronics, breadboard kinds of stuff. Use the same approach. And these are some of my favorite materials. 4 gigapascal, almost a 4 gigapascal modulus. Glass transition temperature, 230 degrees Celsius. Pretty studly for a material. Low dielectric constant. Used in a lot of 5G telecommunication, last mile, terahertz, gigahertz-like communication. Inkjet kind of manifolds. And then one of my favorite applications. This is this Microfluidic, you see the channels device is in this thing about the size of a loaf of bread, designed by NASA. These are the first autonomous untethered vehicles circling the International Space Station, taking photographs and the like. And it uses compressed gas for propulsion instead of combustion. And it is all designed with our materials. Polyurethanes, polyureas, the gift that keep on giving. You vary the soft segment, hard segment, chain extender, a wide range of properties. And you can get into elastomers to rigid materials, depending on how one tunes the chemistry. Rigid materials, these rigid polyurethanes, can have ductile deformation. It could be a linear step growth polymer with a light network of this radical system. And these materials show yield and ductility. High impact strength with high TG, or you can have the more rigid systems. Really opens up all sorts of automotive and electronics applications. Elastomers. Nobody's got an elastomer that's 3D printable, that's got worth its salt in properties. And this really opened up all sorts of applications, from elastomers with a TG well below room temperature, so it's energy returning, or a material that's got a TG closer to room temperature, so it's got damping characteristics. Think about a happy ball and a sad ball. You know, a happy ball, you got a ball made out of this, you drop it, it bounces back up, it's happy. Sad ball, you drop it, it stays on the floor. We have those materials based on molecular interactions in glass transition temperature. But here's where things get really fun. And as a chemist, we always, we cut dog bones, that was pain, cast films. And you always thought the properties of a polymer or a part were derived from the properties of the polymer only. And that's true. But when you get into this digital world, you can have one material with a plethora of performance characteristics by architecture at the lattice level. You can have materials that are stiff or energy absorbing, low stiffness, good for static conditions and comfort, energy return, and you have gradients. And so actually the software for designing gradients of lattices never developed because people couldn't make these things. No one needed it. So Carbon, we developed all this software. It's a huge software operation now to have this and the finite element analysis to tailor with these materials to get you the properties you want. And you get into all sorts of amazing new kinds of structures and avoiding struts hitting one another and designing all these things, or designing a part that not only has the right mechanical properties, but the right orientation and the right lattice structure so that when it's spun, it cleans properly. The digital world allows you to think about performance of the part and its manufacturability. You don't get that easily without being in the digital world. So that's a look back. And it's a platform for making things. And I'm going to play a little video here to reinforce what I just talked about. Oh, we lost
who believe good enough is never good or enough. Those who pursue excellence for themselves and for our planet. At Carbon, we apply our craft using science and technology to push limits and realize products unmatched in performance. Our difference is one you feel, and it is light years ahead of anything else out there. You feel it in running shoes that control energy with every stride. Saddles that enhance your performance and comfort mile after mile. Helmets that increase your protection every time you take the field. Clear aligners and dentures that improve oral health and give you more than a few reasons to smile. Crafted by Carbon is a promise. It stands for dedication and focus to crafting what you and our planet truly need. Ongoing creation of amazing answers to our toughest questions. We salute the leaders, dreamers, and doers who keep creation in motion, who boldly imagine a brighter future and craft it every day.
So it's a platform. Different classes of resins open up different market segments. It doesn't take long to figure out whether you got a material and a process and an economics to make a running shoe, and then you can scale. Automotive takes longer. Regulatory standards and internal standards for quality standards takes long. So I think of these as almost ranked from a regulatory performance point of view. Almost every NFL player has got a personalized headliner. Heads get scanned, so these become mass customized products. A lot of D1 athletes are wearing the helmets now. All fixed-wing aircraft for the military, except for the F-35, are all wearing liners derived from this. This has scaled. This is the examples, or 3D printing has actually transitioned heavily from prototyping into manufacturing, large volume production. The one area I want to just click down on for you is dentistry. We spent a lot of time in this space. Invisalign created a category of digitally printed models, a whole new industry. Their patents expired a number of years ago, and now they have 50% market share of the industry they created, and we basically drive the majority of the rest with our approaches. But the product I'm most proud of is the world's first FDA-approved 3D printed denture. There's 36 million Americans that don't have any teeth. There are over 100 million Americans that are missing a tooth. This is a huge issue for upward mobility. It's hard to get a job. You can't present properly, eat properly, speak properly. And I've got a video to reinforce what we do here.
For the last 45 years of delivering dentures or longer, there was always an unknown. When patients are looking for a denture, their biggest complaint is that they don't fit.
You think of denture making as a craft, I need a craftsperson. And Carbon can do it.
Taking a lot and making it less is what a mill does. Taking nothing and making it something is what a printer does. We don't want to make molds, we don't want to make jigs, we want to make final products. And when you make final products from the milling process, it is far less economical than when you make final products from the printing process.
There's three basic things. There's fit, there's comfort, and there's function. 3D printing brings all of those together. The accuracies in fit, comparably speaking to what was done even 5 years ago, has become so much higher in impact for patients and for clinicians across the country.
For somebody that makes dentures day to day, it's transitional, it's transformative. A lab powered by Carbon will allow me to make probably the best denture ever made.
So we've got a lot of people wearing these. We're passing around dentures. They're not my dentures, so don't feel inhibited. Typically, handcrafted dentures, you're in a chair 8 different times for it to be perfectly fitted. This is a world of digital internal scanning, digital products, 2 chairside visits. It's significantly cheaper, and it's transformative of how, it's going to revolutionize access and dental care. So that's all looking back. When I look forward, I think about opportunities in 3 big buckets, and I know we started a little bit late, but I'm going to try to go through some of this. But advances in the printing process. We still want to go faster. We want to make smaller things, and we want to do multi-material printing. Those dentures I'm passing around, the teeth were printed separately from the base, and they were glued together and then buffed. Advances in resins. We want resins that are electrically conductive. We want resins that are more recyclable or biodegradable. Lots of opportunities here, new properties. Rubber toughened systems. And then advances of software comes in a lot of different ways, from scanning to manufacturing software, but we spend most of our time thinking about the operating system, the digital twin of the process, and going forward. But let me start with high resolution printing. There's amazing things that people are doing in research, especially with direct write tools, to make unique products that are opening up all sorts of great opportunities. Very few of these look scalable based on the methods of fabrication. And there's an opportunity for making at scale a lot of small things. So one of your own, Kai Wynn, one of Charles's people, her project and my transition to Stanford was focused on, let's build a printer with a much smaller pixel projection. So the carbon printers have a 75 micron pixel projected at the build surface, the M-class printers. The L-class printers, it's 162 microns. Kai Wynn and team built a printer down to 1.5 micron. So a red blood cell is 8 microns, put this in context. And that took a team of people thinking about the projection optics, the fluid mechanics, the reaction engineering, understanding the process in great detail, and some in situ process monitoring. And just to show you the fruits of their labor, we always like to work on the Eiffel Tower. This is the Eiffel Tower in the carbon printer. This is a version of the printer with 30 micron features. And then you see that little guy right there? That's with the 1.5 micron features. And where we're going with this, and I'll go into a couple of deep examples, but huge opportunities in microelectronics, in back end of the line packaging and chip-to-chip communication, cooling chips, fan-out structures. You know, lithography and microelectronics, my PhD was in lithography with Jim McGrath. That's 2D patterning, everything's X, Y, and the Z is by layers. When you do fan-outs in lithography, it's every step is a step. You go down and over, down and over, down and over, and you know, opportunities for going at angles and open up new structures with that. MEMS. Most MEMS are made using the tools of the microelectronics industry, etching silicon. A lot of people, you know, silicon's getting thinner and thinner, and people are going thinner and thinner, but how do you make something from 1 to 1,000 microns? It's challenging, and we want to open up that space in a lot of different ways. Particles. I spent a long time talking about particles in my career. We were molding particles using an imprint lithography approach, offshoots of John Rogers and George Whitesides. And I talked a big story about print. You mentioned print. I talked a big story. It was compelling, somewhat. I think at the end of the day, we only had 12 shapes because we needed a master template etched in silicon. And my son actually broke one of those templates in my lab. All the grad students like, thank God it was him. Because there was $15,000 that went by the wayside. We're still in love with particles, but we want to 3D print them now. And so we're doing a roll-to-roll clip process with high-resolution printing, running a film through. And this is Jason's work. He's a chemist, which is fun because he's doing a lot of mechanical engineering stuff. But these are some of the particles that we're 3D printing. This is in Heinrich Jaeger's lab. So these particles are caught in a node of a sound wave, so we can do some good imaging. And Heinrich is looking at the assembly and the physics of particles and particle jamming. But we're making amazing things that we can just iterate on these because it's just light and we just do designs. So here's some simple particles fabricated in this roll-to-roll process. These geometries could be molded. And that's straightforward. Not sure why you'd 3D print them. These get a little more complicated. You'd have to have a two-step molding process to make some of these. And getting alignment and doing the second step can be challenging. But we're now 3D printing these things. And we're starting to get in shapes that it's hard to imagine molding some of these. And you can see the length scale that we're pushing the geometries on these. And really getting in some interesting objects at this length scale. And doing it in a lot of different ways. And thinking a lot about scale up of these particles and the kinds of masses that we could make with one printer using this approach. So we're getting into this. So we're getting back into the particle world with new kinds of shapes and opportunities for doing that. You can ask me about the killer apps later. Microneedles. I think all of us are vaccinated, or at least we're probably got antibodies by now if you didn't. The target for the vaccine are the migratory immune cells in our body. We have 100 to 1,000 times more migratory immune cells in the dermis of our skin than we do in our muscle. But they put the damn vaccine into our muscle. It missed most of the cells. It worked, but you put a lot more in because there's very few cells there. It would be way better to put these where the cells are, the target. Challenge is intradermal injections take a very talented clinical person to do it. It's painful putting a large volume of liquid into the skin, and people just don't do it. When the monkeypox vaccine was needed, there was a shortage of the vaccine. They cut the dose by into fifths and gave intradermal injections to allow people to survive because there was limited vaccine availability. So we're interested in designing microneedles, and the world has been doing this, Mark Prausnitz and others, but it's never turned out to be a reliable and repeatable dosage form. So our first foray into this was our modest resolution printer, where we made these little cones. And we did a free meniscus coating, dip coating operation, where we would coat this plastic with an aqueous solution of an antigen or adjuvant in a sugar solution. The water, you dip it in, it would drain, water would evaporate, and you'd have the coating of sugar or a polymer on the needles. And then you could press this into the skin, and you could do a vaccination. And we showed a couple years ago now that we could get a 50-fold increase in antibody response, delivering the same vaccine into the dermis than you would into the muscle, just by taking advantage of the precision delivery. Now, these microneedles that we worked with back then were coated, had to be coated with a polymer because, and it was wasted, and it would slow to dissolve, but you couldn't use the normal sugar formulations because sugar is not a great mechanical, it doesn't have great mechanical properties. Think about a 2-day-old glazed donut with sugar dropping onto your blouse or whatever. And when you insert these things under the skin with sugar, it sloughs off, and it contributes to the lack of being reliable, repeatable dosage form. With a high-resolution printer, we can now make amazing structures that can be a cage that can protect mechanically fragile materials or liquids. And so we could sequester droplets by controlling interfacial tension and having a droplet sequester, and now we can inject liquids into the skin in an array of microneedles that are pain-free. These are less than a millimeter. Or you can take that liquid and freeze dry it, lyophilize it. And the COVID LNP, lipid nanoparticle vaccine in dry state, is stable at room temperature for 3 months or stable at 4 degrees Celsius for 6 months. But there's a huge cold chain, supply chain issue when it's shipped in liquid form. So this opens up global access and opportunities. And when you can have a dry product, you can insert that into the skin and have your own interstitial fluid, the clear liquid in our bodies, reconstituted in vivo and deliver it directly. And so we've got a big program for measles and rubella, COVID vaccines, all in dry form using these microneedle arrays. I'm going to pivot to a different topic now. CLIP, as I showed you, is drawing liquid into the gap. And the liquid, as it's shown in cartoon form here, is coming in from the periphery of the part as we print this cone. Top-down view, you see all the liquid coming in underneath it. This is still a mass transport limited process. The chemistry will go way faster, but this gap is between 20 and 80 microns depending on how you run the process. So we've envisioned a process that now uses a mechanical injection of liquid through the platform, through a microfluidic channel that's dynamically created, and it goes into the gap. So now we can push liquid, not rely on atmospheric pressure and suction, like drawing liquid up a straw, but we're going to mechanically push liquid into that gap. And you can imagine you can design all sorts of innervated fluidic channels into the part and distribute it based on a lot of different criteria. And you could also imagine putting different liquids into this region. And we anticipated another order of magnitude or more in speed, the opportunity getting into viscous materials, composites, and do multi-material printing. And this is a work by Ian and Gabriel. This is Ian Coates, Jeff's son, and Gabriel Lipkowitz. And we just published on this work. So when you look at this process and you look at the fluid flow by clip, we have the lowest negative pressure in the middle of the part at any given instant. As you pull the part up, creates negative pressure, liquid's being drawn in. But when you think about injection clip, we have liquid coming in this direction, and the fluid flow is in and out instead of from the periphery in. And this changes a lot of things. And what's cool is we can do clip and I-clip at the same time. So imagine making a part where you needed 10 milliliters of resin an hour. I'm just making up a number. You could have all 10 milliliters coming from the periphery of the part by clip. Or you can have all 10 milliliters delivered through the port, through the microfluidic channel, or some gradient mixture of the two. And the mixture of the two would have stagnation zones underneath the part as liquid's coming in this way, coming out this way. And it's a beautiful fluid mechanics study. And there's a Stefan adhesion force between the part and the window. There's a lot of really interesting. Eric Jacquet is not sleeping at night. He's having too much fun thinking about this. What I like to think a lot about is the speed of printing and the liquid adhesion, the Stefan adhesion force. When you have a part in contact with a liquid film between a solid surface and a solid part, it's hard to pull them apart, right? Just think about a drop of water between two plates of glass. That's what we're doing, pulling it apart. And if you put a load cell and you measure the forces, and we put a load cell on the platform and you raise the platform up, there's this your negative pressure created and liquid flows in. So if you have a wide part, you pull the stage up, you stop it, and you watch the fluid flow in. There's a stress relaxation as the liquid goes in and it reaches quiescence. Then you pick the platform up again, another micron or 10 microns, and watch it relax. Well, depending on the diameter of the part, there's less, if it's smaller diameter, there's less force or load on this platform. Well, when you inject liquid, that goes away. In fact, it can be like a rocket ship. You have to hold it down, right? And this allows printing to go way faster. And you can eliminate the supports. You saw those dentures with lots of supports on them as it was coming out of the printer. Here's the Stanford Bunny. It's got some history, and I don't even know, I'm a chemist, but everyone revels on the Stanford Bunny. All the supports to make it. When you inject liquid and you avoid the adhesion, and you innervate the part with this fluidic channels, you can eliminate the need for these supports. And in fact, we've designed a software now where you can shut off the ports, just close it off with light, and push the liquid in different directions. So we're designing all the software to develop these kinds of structures. Okay? You can also do multi-material printing. And not Gulf War, but the Ukrainian War broke out. We added St. Sophia's Cathedral. We're printing different liquids in different regions. And you can make really interesting multi-material. Right now it's just different colors. And we're getting into different mechanical properties and materials. Okay. Well, what's the killer app for injection clip? I'm not sure it's multi-material printing, or it will be. We got a lot to study. To me, it's making negative spaces. The killer app is making nothing. Feels like a Seinfeld episode. But no one 3D prints microfluidics very much with SLA light-based processes. Because as you print a layer, and then you print a layer, and then you go to print a layer that's got a negative space, and then you print the next layer, the light will cure that resin that's in the previous layer that you didn't want exposed. And this gets exasperated when you go to smaller and smaller features. You can control the light in the XY plane with pixels. That's easy. That's easy. How do you control light in a Z direction? I don't know how to do that very well. You can put all sorts of opacifiers, but then your cure rates go down, and it's a problem. We're solving this with fluid mechanics because the resin coming through the port is fully oxygenated. And we can deliver way more than we need at the build surface and keep the amount of resin or the amount of light that exposes that resin to a minimum and avoid curing the channels. So this is work by Ian, And now you see a vertical channel. You don't have overcure issues on a vertical channel because light's always going vertical. But as soon as you start making a channel that deflects in an angle, when you start having the light come out, you have increasing difficulty to print the channel to the point where this horizontal channel will overcure. Well, we compare clip versus iClip, and you see we can't resolve the channels with clip. But when we're pushing resin through the channels, we can. And now we're printing microfluidics. And we're combining microfluidics and microneedles. We're putting plumbing. And this complexity is free. It's still going to be 10 cents for a little part. It's just the mass of the resin. So we're having all sorts of fun opening this space up and making all sorts of neat structures, controlling flow. We're very interested in using these to deliver liquids into the skin and withdrawing interstitial fluid. We have more interstitial fluid in our bodies than we do blood. And a lot of the same biomarkers that are found in blood are found in interstitial fluid at different concentration ranges. And it's a huge opportunity. And so let me share with you, and for lots of young people, often we get pulled into like director meetings. Nadia will say, all right, come in, pitch your idea, you got one slide. All right, so you're going to see you can see an example of a one slide. It's going to look like 6 slides, but this is the art of presenting stuff to directors. So this is our pitch. This would be like an ARPA-H pitch. Making things from 1 to 100 microns easy and gigascalable. Gigascalable for us is a room half the size, 250 printers, 3 months, 1/4 of a year, we can make 100 million things. And we do that by a combination of high resolution clip and injection clip. Okay, that's making things. What do we want to do? We want to disrupt phlebotomy. Maybe Theranos had it right. Except for the fraud. And they went after the wrong circulation system. The opportunity for monitoring ISF. Nobody draws blood from children unless you have to. It's difficult to draw blood from elderly. There's a huge opportunity to massively increase the frequency of understanding the state of somebody by looking at interstitial fluid in a pain-free way. Imagine walking into a Walmart, putting a patch on, doing your shopping for an hour, leave the patch at a counter, and have a service where you're constantly looked at in a much higher frequency for precision health and understanding the deviation from healthy to the earliest stages of disease onset. Huge opportunity there. Imagine combining these microneedles with new kinds of biosensors. This is work with Tom So using DNA aptamers, a photo sensor, and combining and not just looking for glucose. So continuous glucose monitoring is taken off, uses a glucose oxidase enzyme and electrochemical techniques. We're interested in optical techniques and not just in designing DNA aptamers, not just for glucose, but think about cortisol and ATP and all sorts of molecules to get just wearing patches and really amping up that. We just launched a company in this space called IGAN that's doing that. And then I already alluded to this, microneedles for vaccine delivery and drug delivery to the skin. So lots of opportunities. 6 slides, all embedded in one. So let me end there. We really love this field of digital fabrication, digital manufacturing. The promise of 3D manufacturing has been on everybody's radar, Industry 4.0, for a decade. Robotics, AI, sensors. I think what's held it back is not having the linchpin. It's how do you make things digitally? And at least in the polymer side, I think that's changing. When the unmakeable isn't, end-use parts economically at scale really unleashes the power of Industry 4.0. So with that, let me end. I want to thank you for the invitation and be happy to answer any questions. You got a couple minutes? No? A little late, okay.
I think that we can have time for more questions and discussion, if that's okay.
Happy to.
Just a little later, I'll be respectful, people who have other appointments coming up. So I would really like to thank Professor DeSimone again for an interesting lecture, but also showing how you can bridge science, translation, technology to really do what we do here at Beckman. Break barriers, be forward-looking, and think about what's coming next, and then do that thing. So let's thank Professor DeSimone.
Great, thank you. Thank you.
I also want to thank Rana and Hans and the Smith Group again for sponsoring this lecture, and we encourage all of you to join us in the atrium now for the reception and continued conversations. So, thank you.
All right.